So the first problem, basically you need to know that what goes into cosine doesn't have units, and what comes out of cosine doesn't have units. If you have those two things clear in your mind, it's fairly easy to figure out that the units for A must be meters. The units for phi must be, well, 1, or you could say radians, right? They're added to omega t. They must be unitless, dimensionless, rather. And then on the other hand, the product of omega and t must have no units, which means that if t has units of seconds, omega must have units of 1/seconds. Any questions about that one?
If I put degrees, am I wrong?
Yeah.
What if we said phi was a constant?
If you say what?
Phi was a constant.
Phi was a constant.
Which is
Sorry. I would prefer 1. But, I mean, constant. Well, I mean, 1/second is constant. I mean, I don't know about constant. All of the units are constants, right? I mean, unless you think the constants are changing. That's not something I've done in here. That'd be really complicated, right? If the idea of a meter was different days. I probably have to take points out for constant. All right. Because I don't think that pins down to units. That would apply to any unit. But I probably won't take off as much credit as somebody who puts meters. Putting meters for the units for phi would be far more offensive to me. Constant means you have the right idea. I would take off not much for that. Unitlessness.
I did
All right,
that
so
too.
what's that?
Is that okay then?
I mean, if you said phi was unitless, that was fine. Okay, so problem 2, I asked you to find the angle that the vector A, which is given, makes with the positive y-axis. So dot product's your friend here. On the one hand, we have a dot y hat is -2, because the only thing that's non-zero when you dot with y hat is this term, and it picks up the -2. And on the other hand, that's equal to a times cosine of beta, where beta is the angle between a and y hat. Of course, a is the magnitude of a, which is the sum of the squares of the coefficients square rooted. So that's 3 squared is 9, -2 squared is 4. It's hard to see it, but there's a 1 here. 1 squared is 1. You add these together, you take the square root. That gives you square root of 14, divided into -2. And if you calculate your strokes later, you get 122.3 degrees. Any questions about this? Probably not. I hope a lot of you got this problem. I hope. Now, problem 3 is probably a question that you hadn't been asked before, but it's certainly within your power to answer this question. I mean, all you need to know are the things we went over the first couple lectures, and you just have to kind of think it through, do some algebra. So ABC is what you're looking for. You know that a dot x hat is whatever a is, so that's 3. You know that a dot y hat is b, so that's -4. I mean, if you just started by looking at the given information and wrote down that a was 3 minus 4c, I'd be fine with that. I'm just explaining to you why. Specifically, you have to have 3 and -4 in the first 2 components. Is because taking the dot product with x hat and y hat tells you what the x and y coordinates are. Something you certainly should have noticed as you studied the material. Anyway, we also know that the magnitude of the vector is 10, right? But that's the sum of the, that means that 100 is the sum of the squares of these. Well, 9 plus 16 is 25. So that gives me 100 is equal to 25 plus c squared. Solve for c squared. Get 75. So plus or minus square root of 75. Either one of those values gives me a vector of length 10, which has, 3 and -4 as x and y components respectively. There are 2 answers. Yep.
So are you going to take off points if we only gave 1?
Of course. I said find vectors.
Okay.
Yes. So, I mean, how many points would I take off? I don't know, maybe like 70%. Kidding. Yes.
Is it okay if we left it square root of 75 and wrote both vectors?
Yeah.
Less than that.
I think I would tolerate that there. I'll tolerate it right up until the point I don't. So here it doesn't offend me for some reason. I can't exactly quantify when it offends me, when it doesn't offend me for use of a decimal. Like if you're asking me to define exactly the demarcation, the line on the sand, at which point I'm offended by you not giving me a decimal answer. I know when I see it. This isn't it, but yes.
Once if you wrote it as like 4 vectors, plus or minus on that.
Yeah, it'd be fine. As long as you've indicated that there are 2 vectors early, I'd probably got points. Let me stop talking about what I'm going to take points off for. Let's just talk about solution. Otherwise, we're just going to talk about points all day, which is not that interesting. I mean, it's kind of books. So. This looks just like really similar to something I did before. I have a strong sense of deja vu about problems before. What is it?
Problem 4?
What is this? It's a WebAssign problem, that's right. So yes, this is exactly a WebAssign problem, pretty much, right? I mean, you might have had, instead of northeast, you might have had southwest here or something, right? But this was in fact one of your WebAssign problems. The way to solve it is very simple. The velocity of the canoe relative to the Earth is equal to the velocity of the river plus the velocity of the canoe relative to the river. You are given that the velocity of the canoe relative to the Earth is in the northeast direction, which is 45-degree standard angle, so there's a unit vector in the northeast direction. You're given that the speed relative to the Earth was 0.25 meters per second. So there's that. And then the velocity of the river was 0.55 meters per second east, so that gives me this 0.550, that's my river velocity. And then I just solve, subtract the river velocity to the other side to get the velocity of the canoe with respect to the river. And out pops this vector over here, minus point. And then what I have to do is, of course, find the magnitude. As I asked you for the magnitude of standard angle, so the magnitude squared is sum of the squares, which turns out to be 0.413 meters per second, and the angle turns out to be 154.7 degrees. Now I know that's the right angle because I drew a little picture over here. I said, okay, well, I've got a negative x component, I've got a positive y component, so it's got to be up in here somewhere. So my angle, my standard angle, ought to be somewhere between 90 and 180. So that's where I got the 154 from. I mean, specifically, you can calculate the inverse tangent of the ratio of the y to the x.
If we got the northeast vector and the east vector.
Problem 5 was calculus. So, first of all, if I have t times a vector containing t, I mean, there's a couple of different ways you can go here to calculate the acceleration. Either your first step is to multiply the t inside, right? So you have 3 functions at a time and then you can differentiate. Or you can look at it as a function times a vector. Now there's a product rule for functions times vectors. If I have f of t times a vector a of t and I differentiate it, the product rule for such a thing is this: df dt times a plus f times dA dt. So I'm using this product rule to do the calculus there. Now, of course, that's not absolutely, you don't need to do that way. You could, of course, just multiply t inside and differentiate each component. But the point is, at some point or another, you have to face the product rule, especially as it concerns the y component, because if I multiply the t inside, I get at cubed, bt times sine of t squared, and then bt. Yes, sir?
You drop the constant in the problem, the constant c.
Oh, man.
No, it's still in there.
That's funny. I picked it back up in the position part. Yeah. Oh, well. Take some of my points off. Yes, there in fact should be a, yeah, I gotta fix this. I forgot to put the ct squared here, 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 here. There. And the chain rule brings, there's some c's missing up front too, right, for the chain rule. Don't look at your titties. Okay, so this one's better, I think. So apparently I can integrate, but I can't differentiate. Okay. Great. So all I did was I multiplied the t inside the vector, which gave me at cubed, plus dt sine of t squared, and then dt. The integral of at cubed is 1/4 at to the fourth, so we can all agree about that, I think. The integral of bt is 1/2 bt squared. I think we can all agree about that. The middle one, how did I go from here to here? What did I do? What sort of dark magic today?
U substitution?
U substitution, right. I let u equal to ct squared. Okay, so if you do that, that ends up making you divide by 2 in c, because there's a c here. So the 2c is from the u substitution. Anyway, you can judge the validity of my antiderivative by differentiating this, which just takes a second in your head. That's sine of ct squared times 2ct. The 2c cancel, it leaves you with b times t. There's a minus from the differentiation of cosine. Those minuses cancel or come back to bt sine ct squared. Of course, you can write out your work if you want to, but I don't care. It's calculus. But I do expect you to get the right answer here. Anyway, plus some constant vector, which we don't know yet. But I tell you that R0 was 0, right? But if you plug in times 0 into this vector, I get 0 minus b over 2c, 0. Which then tells me that c1 is in fact plus this. 0 comes plus this. And so then that gives me this position function, 1/4 at to the fourth minus b over 2c cosine of c squared times 1, and then 1/2 dt squared. Again, my current acceleration is wrong. I need to fix it. Okay. Or I could take n equal to 1 in my first part. But no, I'm just being defensive. Yes?
We've got t equals 0 in that second term with position. Doesn't it come out to 1 minus 1? So you just cancel. Cosine of 0. So 1 minus just cancels, so it's all 0. And the
Right.
c vector is just all 0.
Yeah, if you put in t equal to 0, you get R0 is the origin. Like I said, it should be, right? R0 is 0, 0, 0. But yeah, if you plug times 0 into here, that gives me cosine of 0, which is 1. 1 minus 1, 0. Okay, problem 6 looks more complicated than it is, right? Problem 6 is actually really easy. So you go 3 kilometers this way, 4.9 kilometers that way, 3.15 kilometers this way. Of course, this picture's wrong. Here's a better picture. 3 this way, 4.9 this way, 3.15 that way, right? Kind of matters for your consideration of the standard angle, right? We should be looking for a standard angle for the displacement somewhere between 180 and 270, right? So I just add those displacement vectors to get the total displacement. That gives me minus 4.9, minus 1.5. I calculate the magnitude. And I calculate the standard angle by taking 180 plus this acute angle, which is kind of tiny. Any questions about this one? Was this familiar? It should have been. This was yet again a WebAssign question. By the way, this, while it was not a WebAssign question directly, you had many WebAssign questions very much like that one, give or take some calculus. But hey, calculus 1 is something you've all had, so you should be able to do it. I mean, that's the version of reality I live in. So it may be a false assumption, but it's one I make when I'm making tests. So sorry. Oh, okay. So this one, you might recognize this. This is a one question. This is yet again a WebAssign question. Yes. Oh, Bailey's not listening. Just trying to bother. Didn't work. Oh well. So again, you know, to find the magnitude, we take the square root of the sums of the squares of the components, right? There they are. Of course, be careful about units. That one's got meters. That one's got centimeters. So the answers in turn are centimeters and meters. The angle, you know, draw a little picture to keep yourself honest. Again, between 90 and 180, that would be 148.2. I have to subtract that acute angle from 180 to get in there. This one's down here, so I have to add the acute angle to get in there. So right, problem number 8. So if you're not reading this problem carefully, you might be tempted to just add A, B, and C and answer like that. Of course, that would be wrong because that's not what I asked for, right? I asked for A plus 2 times B minus C here. So what you got to do is figure out what A, B, and C are and then do that. So to figure out what B is, what I do is I just say, okay, well, this is my theta 2. Oh man, it's really bad in the scan. It's even worse now. It looked better on your actual test paper, right? A little bit better than that. It's still not too good. So let's see, that was 36 degrees, so 90 minus 36, I hope, is 54.
Theta 3 is 61 degrees. It's just not a scale.
Yeah.
Oh yeah, the drawing's not the scale. That's a given. Never assume that these drawings are to scale unless I don't give you information and say from the drawing, you know. So, but whatever. Let's see here. So that's where the 90 minus 36 is 54. That's how I knew this angle. Down here was 54, right? So that's the standard angle of the B vector. So then magnitude of B times cosine standard angle, magnitude of B times the sine of the standard angle for B. That gives me its components, 8.817, 12.4. Now for C, I decided just to use the theta which I was given, which was 61 degrees for here. Obviously, like you said, not very much to scale, right? Maybe I should say not very much to angle. Anyway, quite clearly, this is in the third quadrant, so both of the components, x and y, should both be negative, right? So that's why I put minus 12 cosine and minus 12 sine is 61, which gave me those two numbers. And then A, well, A is easier, right? 0 minus 8. And then I just let the vectors do their magic. Here's A, 2 times B, minus C, and I just do those things component-wise and add them together, and that gives me this vector. And then the sum of the squares of these square rooted gives me that. It's quadrant 1, right? So I expect an angle between 0 and 90 degrees, and that's what I get. Yeah. Up. Oh, was that picture familiar? It should be. It was from? It was fine. That's right. Okay, I think we're sensing a theme here. A dot C is the magnitude. Okay, so I mean, there's various directions here. You could have also calculated the magnitude of A and the magnitude of C and multiplied by the cosine of the angle, which was given in the picture. I decided it was just easier to calculate the dot product directly, so I did that. That gives me 84 meters squared. Both have units in meters. I pick up meters on meters, which is meters squared. A cross C, well, I know a nice formula for that. That's AC sine of the angle. That's the magnitude of the cross product, which I would much prefer to actually calculate in the cross product than taking the magnitude, right? Like, this is way easier, given the information you have. So I do that, and I get 46.56 meters squared. Finally get the direction of A cross C. I use the right-hand rule. So A, oh, yeah, if I was taller, but oh well. Oh, yeah. A, and to cross it into C, right? So like that. So I'm pointing into the screen, right? So that would be, as I've defined, Z hat is coming out of the screen. It's in the minus Z hat direction, also known as into the page. So, any questions before I lather on? Yeah.
It's hilarious to watch us when we got to that problem when we were trying to shorten our hands.
I didn't look. I was polite. I preserved your dignity. I did not like that. Yes, here's the objectionable web assigned problem about dropping eggs on physics professors' heads, which is something I didn't really need to worry about since one of you is possessor of many eggs. But, so my approach to this problem is to drop in the egg from the building to this height of 1.6 meters, right? So really the question is, how much time does it take for that to happen? So to figure out that time, I just write the equation for an egg dropped, which is 52 minus 4.9 t squared, because it's dropped, it's not thrown down, right? If it was thrown down, there'd be another term here of, you know, minus v naught, I mean, whatever. So if it's thrown down with 10 meters per second, I would have 52 minus 10t minus that, right? But I don't, it's dropped, so there's no velocity, initial velocity term. And I just set that equal to 1.6, which is where the professor's head is, and then solve it. So that gives you t of 3.207. Okay, so then that's how much time it takes for the egg to drop from the building down to that level. And the professor is just walking at constant speed, minding his own business, right? So if you're up there and you want to drop it such it hits his head, that means that you need to let him walk that much time as the egg is dropping, right? In order for them to intersect. So you just take that same time, multiply it by the speed of the professor, and that tells you 1.04 meters away is where you ought to catch your nefarious plan. Yeah, yes, hatch. Unintended pun, but there you go. I'll take it. Take a crack at it. I don't like what we're starting here.
I don't know, the sharks are pretty funny. I didn't say they're pretty runny.
Oh, and this is a problem you've never seen before, right?
Of course not.
Okay. No, that is also a web assigned question. By the way, this test is by no means a binding contract between me and you that I'm always going to ask mostly web assigned questions on the test. My point to you is just that those problems matter and you should try to understand them. Because they might be on your test, I don't know. All right, anyway. So here's a little bit more. Now, I told you guys, and Dr. Kilpatrick also told you, that I was basically thinking of it being thrown from the edge of the building. So anyway, the point from which it's thrown to the point at which it lands, that's the distance, which is 18 meters. To make the problem more interesting, I could have told you it was thrown from a height of 1 meter, and then you'd write 19 instead of 18 in the y equation, right? But anyway, so if it's thrown from a height of 18 meters, I need to figure out what's its initial y velocity. To do that, I take v naught, which is the speed, times the sine of 33. That gives me the y component of the velocity, right? Now the x component is cosine of 33 times the speed, which gives me 19.29. So the x component of the velocity governs the horizontal motion of the projectile, whereas the y velocity determines how far it goes up, right? And ultimately the time it's in the air. So I just basically have to write down the y equation, standard kinematic equation, on Earth, minus 1/2 gq squared minus 4 by 9. Set that equal to 0. Solve this quadratic equation. You get two solutions. You get 3.583, or you get minus 1.025. This obviously is what would come mathematically from continuing this backwards, right? Like if you were standing, if the building was hollow and you had thrown it from the ground at such an angle that it just barely cleared the building here with that speed and that angle, this is what time it would have been. It would have been 1.025 seconds before it got to this point right here, right? That's just the mathematics. It's taking you back in time to where you conceivably could have been on the ground to recreate that situation in the air. That's obviously not the time we're looking for, right? The hit time is the larger time. And so to find the horizontal displacement, I just take that time, plug it into the x equation, voila. So. The rocket car. I like the rocket car problem. It seems hard, but it's actually easy. Now, it is very hard if I don't tell you that it starts at rest, but thankfully I remembered to tell you that. I need to add that to the problem statement. But given that it starts at rest, you can just apply the timeless equation twice, right? So, first of all, the velocity when the rocket motor turns off, let that be v1. So v1 squared is equal to v naught squared plus 2 times acceleration times the distance that it travels. Well, we're given the distance it travels during the accelerating period is L, right? So that's why I put this L here. The A is 3g, which gives us 6g over here. Not currently available from Verizon, but this is 0. Don't worry, we'll get to 6g eventually. So v1 squared is 6gl. And then that sets up the second part of the motion, which is from the point the motor turns off and while it's braking to a rest, right? So the final, if it stops, then the final velocity is 0. The initial velocity is v1 squared. The acceleration is minus g, so that gives you minus 2g delta x. Delta x, I don't know. Kind of a point of the problem is what is that distance? But whatever distance it is, you have to have 0 is equal to 6gl, which I know from there, minus 2g delta x, and a little bit of algebra later, you figure out that delta x is 3l, so l plus 3l gets you the total distance, 4 times the l length. Es bueno? Alright. So I asked for you to derive the timeless equation. There is another more painful way to do this. But the basic assumption, of course, is definitely true. If the acceleration is constant, right, and it's one-dimensional motion, I don't know. If you don't say it's one-dimensional motion, I don't care. What I do care is that you said that the acceleration is constant. If the acceleration is not constant, there might be some sort of timeless equation, but it's not this one. Okay? Something more complicated. So, acceleration being constant is the assumption I'm looking for. And then once you know that, my favorite way to do is to separate variables and integrate. The other way to solve this would be to take the two kinematic equations, one for velocity, one for position, solve one of them for time, say the position one, plug that in, maybe solve the velocity one, and plug that into the position, thus eliminating time. And about a half page, a couple lines of algebra later, you'll come to the timeless equation. But, you know, there is another way of deriving it, but I prefer this way. Finally, Kakashi. So on level ground, Kakashi can throw a particular ninja tool a distance of 50 meters. If Kakashi throws the ninja tool while riding on a sprinting hound, running 20 meters per second, then how far can Kakashi throw the tool? Ignore resistance, assume both throws are optimal, and that the throws begin and end at the same height. All right, like I said, perhaps the target is mighty guy and a large turtle, or perhaps a large cat. And I'm also assuming that Kakashi has the same throw strength, like in both instances. So he throws at the same initial speed both times. So first of all, you can figure out how far he throws on the ground, just standing there. That's not hard. You can use the range equation, right? We know 45 degrees gives us the optimal throw there. So that tells you what the speed is that he can throw with. You can actually find a number for that without any kind of, here's my sloppy solution. I haven't had a chance to write it very cleanly yet. So here's my, so there's my ninja hound, and there's your Kakashi.
Should we put a mask on?
I don't know, I don't really draw one stick figure. So, that's my mighty guy, which is, I don't know. Anyway, as you can see, it's a turtle.
Or sparkle
Yeah. Anyway, so he's standing on the turtle shell. This is mighty guy. I don't know why I'm correcting this. Anyway, so the velocity though, I can get from 50 meters is equal to, of course, sine of 90 degrees gives you the maximum, right? The biggest sine I ever can get is 90. Sine of 90 is 1. That's it. That's the biggest. So I can solve that for V naught, and you get the speed at which Kakashi's throwing is 22.14 meters per second, right? Then the question becomes, so what's the equation for x and y when he's on the hound? Well, then I got to use the moving frames idea, right? So to find the velocity on the Earth with respect to, for Kakashi throwing it on the hound, I would take the velocity of the hound, which is 20 meters per second. And just common sense, he's clearly going to be able to throw it the farthest when he throws it in the direction in which the hound is running, I think, right? Yeah. If you want to throw a ball as far as possible and you're on a train, like, should you throw it with the direction the train is going, or should you throw it the other direction? Yeah, like in the direction you're going. Actually, okay, anyway, so 20 meters per second plus the x component this is the x component of Kikashi's speed with respect to the hound, right? So if he's on the hound and he's throwing it with his maximum throw, his v naught speed, which we already figured out there, v naught cosine theta, and that's the theta relative to the hound, right? Like I've drawn here, that's theta with respect to the hound. That would be his x times time. Now y would be, the y velocity is the same in both, right? The hound's y coordinate and the Earth's y coordinate, they're the same. They're not changing, right? Same y. And so there it is. V naught sine theta times t, that's the y velocity that he throws it up with, right? And then minus 1/2 gt squared. And then you're looking for where that's 0. That's going to give you the time at which it comes back down, right? So you got to solve that equation. Solve that equation to find the time at which it hits. So you can factor out a t, and just like usual, we get the time was v naught sine theta over g. We saw this in the derivation of the range equation, for example. This is the same math. So then what do? I take that time and I plug it back into the x equation. This is, sorry, this is out of order. This is the answer. I just wrote back up in here. You gotta ignore this. Ignore. That's right. If I had like a giant piece of tape or something. Oh, but we should project on top of it. That'll help. Yeah. Oh well, just block this out of your mind. Okay. So down here, I plugged in the time. And then I just multiply it out. Now, what I do is I just factor this constant, 2v naught over g. 2v naught over g, I just factor out front, because it's just a constant. I don't care about that. I want to figure out whether this quantity optimized, right? What does optimal mean? Like optimization from calculus 1, right? The longest. So do what then? So I clean up the formula a little bit. Formula for x is alpha times 20 plus 22.14 cosine theta times sine theta. Yes, sir.
What I did to find theta was I separated out the x and y components of the velocity of the tool versus the ground. So it was like 15 point something versus like 35. And I ended up like, what's wrong with that approach? Taking it, then using that to take the inverse tangent.
We said that the velocity of the ninja tool with respect to Earth is equal to the velocity of the hound plus the velocity of the ninja tool with respect to Kikashi. And we vector added those. One came out to 35.66, comma 15.
I don't know. I have to look at your solutions to think about it.
Theoretically, it's the same thing as what's going on here.
But it ends up with the same answer.
Yeah, so that is the answer.
Well, it's not the same. But I'm not, you guys, I could, who knows, maybe I'm wrong, maybe you're right. Well, let me think about it, okay? But let me finish my answer here, then I won't talk it. So, again, on the basis of the velocity relative with respect to the Earth being the velocity of the hound plus the velocity of the ninja tool, the x component of the velocity of the ninja tool with respect to Kikashi, that gives me the x component of the velocity of that times time should give me the distance in the Earth frame. So then I put in the time at which it hits the Earth, which we figured out, and that gives me a formula just for theta. All right. I then differentiate that to find to set that equal to 0, because that will give me the critical angle, the angle at which x is maximized. And when I do that, I end up with cosine squared minus sine squared here. But I can trade a sine squared for a 1 minus cosine squared, which then gives me this lovely quadratic equation in cosine theta, as you can see, which I can then solve with the quadratic formula to either tell me cosine theta is 0.516 or minus 0.9681. I choose this one, and that gives me 58.91 degrees. Yeah.
Isn't like optimum like which like anything like distance
I was thinking means one is always 45 degrees.
No. It is not the case that 45 degrees gives you the optimum distance for projectile motion in all cases. 45 degrees giving us optimal distance is when we begin and end at the same height, and there's no relative motion stuff going on. I mean, even if you're on a tall building, right, and you want to just shoot off the tall building, get as far as you can on a horizontal plane, the optimal angle won't be 45 degrees.
That was our mistake. We assumed that he would still be throwing it at 45 degrees relative to himself. It would be the same throw.
Yeah.
Could you scroll up to see the
This is
parameters?
re-optimized.
See the what?
The definition of the problem.
Of the problem statement?
Distance of 50 meters. So
Sorry.
I hear you.
great.
So anyway, after the dust settles, I found you can throw it about 121 meters, accounting for the additional speed of the hound. So that's why if you have archers on horseback and the horses can really, I guess that may not be too big a deal, right? Because if you have a good bow, you can shoot an arrow pretty fast, right? The speed of the horse is not really that comparable to the speed of the arrow, is it? Probably not. I don't know if it makes much of a difference. In this case, it made a really big difference because Kakashi's speed was 22.14 meters per second on ground, and the speed of the hound was 20 meters per second, right? So it's a significant boost to the motion. Wow. Anyway, this, of course, was mostly bonus, right? So I'd give you 5 points if you can at least find Kakashi's speed. I might give you more. I haven't decided yet. Kind of depends what I see when I look at it. And with that 5 points, that's 150 points. There's 10 extra bonus points here. So I mean, I know that most people are going to get this. This is the challenge problem. Yeah.
Is this document posted online?
Not yet, but I will. Questions, comments? I know, no comments. what am I saying? No, I don't want your comments.
What matter of ninja tool is this?
What kind of ninja tool? I don't know. I can't spell those words, so I just decided to say ninja
Are you
tool.
talking about like a ninja star or like a ninja that's just kind of a jerk?
Could be. A ninja.
Dawson's
All right, so I am actually supposed to tell you about some physics today, so let me do that. I don't have much to tell you there, though. I mean, I would like you to read the lecture, read my lecture notes on this. I probably won't say quite all those things in class. I'll try to say enough of them here so that we get the big idea. But we come now to the study of dynamics, all right? What's dynamics? Now, I mean, people will debate which came first, the chicken or the egg here. I don't know. I'm not sure I care. Sorry. But I should care. But basically, this is in a nutshell. I mean, depending on your philosophy, it's all present. Basically, this is the story. Forces cause motion. Okay. Why do things move? Well, classical mechanics says is the reason that this marker is going to leave my hand, fly up into the air, is because I put a force on the marker, right? I pushed on the marker with my hand, and I accelerated it, and that's why the marker flew up into the air. Why did it come back down? Gravity, right? There's this thing called the force of gravity. The force of gravity accelerated the marker back to my hand. Those are forces. Push, pull. The force that a spring puts on a mass is go back and forth, right? You had a slingshot as a kid. The force the rubber band puts on the egg, piece of chewed up paper with spit. I mean, whatever it is that you apply forces to project over distances. Your favorite Nerf gun has got some spring inside of it. The spring force propels the Nerf whatever to go, hit the other kid in the head, eye, whatever it might be. Yeah. Yeah, well, come on, I forgot my theme. Yes, cat, of course. But I don't know. Well, I guess no. I mean, Nerf is too good for a cat. When I think cat, I think at least paintball. I'll take circus mallet. I mean, so what is a force? I mean, what's this idea? Well, here's the basic idea. Suppose you have a frame of reference. Suppose we have a coordinate system. And in particular, I'm thinking of a rectilinear coordinate system. It's laid out by 3 orthogonal directions, right? You take the unit vectors in the direction of increasing one of these coordinates. The dot product of these respective unit vectors is 0. They're 90 degrees separated. We also insist that, typically insist that they form a right-handed triple. So like if you take the first coordinate unit vector and cross it into the second coordinate unit vector, you get the third one, right? That makes it a right-handed coordinate system. I guess that's not absolutely needed for this, but I usually do. Suppose you had a coordinate system, all right? Then if there's such a thing as a force, here's what it does. The force, all right, and it is equal to, and suppose you just have one force to start with. Well, the force is going to equal to mass times the acceleration. And what I mean here, I'm talking about a particle, all right? So more specifically, there's some coordinate system, x, y, z. There's a particle. I'll draw it in Pac-Man, I don't know, whatever. So there's your particle. All right. There's some characteristic constant associated to the particle called m. All right. And what this idea, this concept of physics says is if you apply the force F to the particle, which I've drawn in Pac-Man, then what happens when you apply that force, right? You don't have to apply it. I'm talking about conceptually apply it. Who knows? That force could be gravity. That force could be the force of the spring. That force could be, it could be the warm summer wind blowing on the sails of some sailboat crossing Lake Michigan. I don't know, whatever. There's lots of different things that could be forces. Don't pin me down as to what exactly a force is. It's a very, very general idea. But this much I can say: if there is such a thing as a force, when you apply it to a particle, in this case Pac-Man, and that particle has what we say mass m, that produces an acceleration a. So maybe it would be more honest to write this equation as a equals to the force divided by the mass. There's what's called inertial mass. This is inertial mass because it describes how the body responds to a given force. All right. All things being considered, if I had 2 Pac-Mans there and I applied the same force to 2 Pac-Mans, I'd get half the acceleration because I'd have twice as much mass, right? Yeah.
Is there such a thing as non-inertial mass?
Yes. Well, that's a question. Conceptually, there's such a thing as non-inertial mass. The question is non-inertial mass the same as inertial mass? Are they equivalent? That's a question you can ask. Now, so anyway, are we clear? It's kind of a, so basically here's a story. If I tell you your mass is 10 kilograms, and I tell you a force of 100 newtons is applied, you can tell me the acceleration, right? So for example, you have a mass of 5.0 kilograms, you have a force of 1.0, let's say 10 newtons, 20 newtons, 30 newtons, all right? And you apply that to the mass, what's the acceleration? Okay, so what we do is say the acceleration is equal to the force divided by the mass. So that gives me 10 newtons over 5.0 kilograms, 20 newtons over 12.0 kilograms, 30 newtons, 12.5.0 kilograms. And what is that? What is a newton, by the way? You told me it's, newton is equal to, you just told me, I forgot already, kilogram times meter over second squared. Right, so if I have newtons over kilogram, put that there. So if you have newtons over kilograms, you cancel the kilograms, and you're left with meters per second squared. Well, that's because otherwise it would be kind of a drag if we didn't get meters per second squared as the units for acceleration, right? Conversely, right? If I tell you you have a mass of 10 kilograms and it accelerates at a certain direction, you can figure out what's the responsible force, right? F is equal to ma. All right, so up till now I've been talking about this as if there's just one force, right? So where is the force?
The force be with you.
The proper way to respond to this question is to raise your hand. Once the dramatic silence is done, then you should say, but professor, the force, it's everywhere. This is how it was answered in my junior level mechanics class. We laughed for like 3 minutes. So well delivered. Good try, guys. It was a good effort, but no, I mean, so, but that is really the question is for a given, body. I said that I threw the marker up, and then it. That was an unfortunate turn of phrase. I projected the marker. Yeah, I don't know. Anyway, I threw the marker up, and I find it is what it is. Now, was the only force on the marker when it left my hand just the force of my hand on the marker? No, it wasn't. There was the force of gravity. It's not like this is an anti-gravity marker in the process of me throwing it. It's just that the force of my hand overcomes the force of gravity, right? And this right there, right? And accelerates it, and then the marker leaves my hand. I mean, it overcomes the force of gravity. So the true, this is the start of the story, but the end of the story is this. The sum of the forces, right? The sum of the forces is equal to the mass times acceleration. Or sometimes we'll just say the net force is equal to the mass times the acceleration, all right? So as we're working problems, you can't just say force is equal to mass times acceleration. That's wrong. Unless that force is the net force on the mass. All right? Now I have one other thing to talk about here today, and then I'll be quiet. This was with respect to one coordinate system, right? The Kakashi problem, right? I had a hound. Right? And I assumed something in this problem. I basically assumed that gravity behaves the same way for the hound frame of reference as it does for the Earth frame of reference. That's actually true, but this begs a deeper question, right? When you change from your original coordinate system to a new coordinate system, what happens, right? What did we learn about the transformation of coordinate systems and the coordinates? What was the relation? You guys remember? How's the acceleration? The acceleration in the new coordinate system, right, was equal to what? It was the acceleration of the coordinate, the origin, right, plus the acceleration. Well, I guess I had the other way. So let's say this is the acceleration of some particle with respect to the Earth. This would be the acceleration of the coordinate system plus the acceleration with respect to the moving body, okay? Moving frame. Acceleration with respect to moving frame versus, say, acceleration. And I'm sorry, this is a very flat Earth comment. I'm talking about the hypothetical, just very boring Earth not rotating, forget about all that. Earth, just think of Earth as a plane, not moving. This is that kind of coordinate, man. So annoying, everything's moving. My point to you is the accelerations would be different if this was non-zero. Okay, so in order for Newton's law to hold in both frames of reference, what do we have to have about the different frames of reference? They have to be unaccelerated with respect to each other. So this has to be 0 for a what's called an inertial frame. So for an inertial frame of reference, if you give me one fixed frame, all right, just give me one, I can find other inertial frames with respect to that one by just looking at transformations which have constant velocity with respect to the given frame. Those are the ones which will agree on the acceleration. Then the question though, even that, is how do you find the force in the new frame of reference, right? If you wanted to compare the equations from one frame to another, you have to do that. These are not easy questions to answer. I'm just throwing it out there. We'll come back to it eventually, but for the immediate future, we're going to be working a lot of problems like that. And so I'm going to stick to that. And maybe once we understand the force is a little bit better, we'll come back to this question of inertial frames of reference and what that all means. I say a lot more about that in lecture 8. You can read it. Yeah, talk about next class if you want. Have a good weekend, guys. You guys ruined my weekend, of course. I had to grade your test.
You ruined your own weekend. You ruining your weekend.